Good morning. My name is Ravi Babu, Assistant Professor in IARE, Institute of Aeronautical Institute of Technology. I am going to teaching about the digital control system. Today in class we are going to seeing the system response in Model 2 in digital control system. Whereas in previous section we see the properties of unilateral jet transform, 4 properties. Now we are going to see the remaining 2 properties and problems. Now I'm going to one of the properties convolution in time domain property. If x1 of k you take, that is in case of time response analysis, that is time domain analysis, x1 of k, if you apply z transform of that one, it is coming to as x1 of z, where similarly for x2 of k equal to x2 of z, then the convolution property shows that x1 of k into x2 of k equal to x1 of z into x2 of z. This is the convolution property. Now I want to going to prove that one, that is x1 of k into x2 of k equal to, if you take for this one, I am going to taking the m equal to 0 to infinity, that is it is a unilateral function now, that's why it is here m equal to 0 to infinity, and here we taking the integrals summations of m, that's why it is coming to as x1 of m into x2 of k minus m. So coming for this one at RH side, so z into x1 of k into x2 of k, that is we are going to applying the z transform this one. So the basis of the z transform formation, starting formation, that is k equals 0 to infinity. Okay, k equals 0 to infinity. The function of this one is, I am taking here this function into z power of minus k, that is the basic formula for z transform. Okay, whereas in this one it is a function of m. Okay, it is a function of m. So here limit is k equals 0 to infinity. So it is applicable for only, and here only for k values, where here x1 of m is there. That's why it is a constant. So I am taking this one is outside of the summation. So m equals 0 to infinity into x1 of m into k equals 0 to infinity x2 of k minus m into z power of minus k. So here m is the only, this function is with respect to m. That's why I am taking the outside. Okay, this is this expression is coming from this one. After that one, we know that k equals 0 to infinity x2 of k minus m minus n z power minus n equal to z into x2 of k into n minus 1 equal to, that is for this one we get the z transform is z transform minus m into x2 of z. So substitute this one into above equation, where this is where it is existing now. Here we have to substitute this one value. So what happened? M equal to 0 to infinity x1 of m into, so it is value is z power of minus m into x2 of z. Again here x1 of m is the, and x2 of z is the, it is the x2 of z. So if you take this one for here, x2 of z is the constant. I'm sorry, x of z is not a parameter of m term. So that's why it is coming to as like this. After that one, this total part is coming to as, this is nothing but x1 of z. It is nothing but x1 of z. Okay, where m equals 0 to infinity, z transform of x1 of z. So by seeing this one, so it is coming to as, it is x1 of z, and here x2 of z is there. So what happened? Z transform of, from convolution theorem, Z transform of x1 of k into x2 of k equal to x1 of z into x2 of z is c. This is your convolution property. What are the applications is there? See the applications here, where x of k is the input function and z of k is the system function and y of k is the output function. Okay, so by using this convolution theorem, we have to make it the output function variables. Output function variables. So what happened? The output of the function is y of k equal to x power of k into z power of k, where you have to apply here z transform. So y of k is coming to as y of z, and x of k is coming to as x of z, and g of k is coming to as g of z, where this g of z is called as a pulse transfer function. Pulse transfer function. We will see this one is after of this z transform concept, and that is z transform. You know the z transform, discrete time systems, differential equations of the differential equations of the discrete time systems. After that one, we see the pulse transfer function. Okay, for this one, we are get the y of z equal to x of z into g of z. Okay, so what happen if you substitute this one into here? What happen if you take again for this one, convert it into discrete time systems? So y of k equal to z inverse of z transform of x of z into g of z. So this is the convolution property here applicable for an open loop control system, open loop plant. Okay, that is, first of all, we are going to convert it into that part into time domain to z domain. After that one, we are going to convert that one into z domain to time domain. Z domain to time domain. Coming for the next one, next property is differentiation in z transform, z domain. Differentiation in z domain. Coming for the differentiation in z domain. If x of k equal to, in terms of converted into z transform, it is coming to as x of z. Then k into x of k equal to, it is coming to as minus z into d by dz into x of z. So coming for the proof of this one, first of all, if you take the function is k into x of k, if you apply this for this one z transform, so the basic formula for z transform we know, that is k equal to 0 to infinity, that is for, this is for k equal to 0 to infinity, but it is unilateral functions into k into x of k. This is the function k into x of k written, and z in power minus k, z power minus k, where in this one also same. I am going to for mathematical calculations. Okay, I am going for mathematical calculations. Here z power of k will be there for minus k. For substituting this k equal to minus 0, so what happened? This is difficult to for finding the mathematical calculation. For that one, I am going to taking the, from here z is common. So what happened? Z is coming to outside. So similarly, k equals 0 to infinity, k into x power k into. So what happened to z power minus k? Z power minus a is coming to as z power of minus k minus 1. Minus k minus 1. Okay. After that one, again I am going for mathematical calculations. That is, I am taking the minus is common. So from our expression, I am taking the minus is common. Minus z equal to k equals 0 to infinity, x power of k. So this k is coming to here into z power of minus k1. So you are making I is minus. This minus into this minus nothing but coming to as above expression. It is coming to plus. Okay. So this is the up to here. You have to understand. Now I am going for the, the concept of the basics of Z transform formulas. Already I have explained in previous chapters. That is, derivative of z power of minus k equal to minus k into z power of minus k minus 1. Minus k into z power of minus k minus 1. So substitute these values into above section. So what happened? Z into x power of k equal to z into x power of k equal to minus z into k equal to infinity x of k there. And what about this one? This one is minus k into z power of k minus 1. Minus k into z power of k minus 1. This is nothing but this value. I am substituting the in above values. So minus z, minus z, minus z, k equals 0 to infinity, k equals 0 to infinity, x of k, x of k. So what about this one? This is nothing but d by dz of z power of minus k. Z power of minus k. We are coming to here summation limits, that is k equals 0 to infinity. K is there. So what about this one? In this one, minus z is for mathematical calculation. Sorry, minus z is 0. So correct. Sorry, minus z k equals 0 to infinity d by dz. It is a function of this one. I am going to taking as x of k into z power of minus k. Okay, x of k into I am taking the inside of this one. For this x of k is going to I am taking the inside. So what happened? D by dj minus z. Again here k summation is for the function of only k terms. That's why it is a constant. So it is I am going to taking outside. So k equals 0 to infinity x of k into minus z. X of k into minus z. So what happened? This total part is so minus z into dz by dj equal to, so what is the formula for this one? This is nothing but x of z, basic formula, x of z. So hence we prove that one is for this one k into x of k, for k into x of k, the z transform is minus z into d by dz into x of z. You have to remember this is the differentiation in Z transform with respect, and here proof will be there. Okay, now I am going to the application of this one, where it is applicable. Now see this one. Already we know z power of k equal to z by z minus 1 whole square. This is the properties already we know. In previous section in table column I explained this one. For this one, we are going to be taking the property, that is x of k equal to k we know. X of k equal to k we know. So find the x of z. Find the x of z. Okay. How can you find the x of z? X of z here they given as I am taking the x1 of k equal to 1. So for this one x1 of k, we are taking the Laplace transform. X of z equal to z by z minus 1 will be there. Z by z minus 1. Okay. So take this one. X of k equal to k into x1 of k. If you apply here limits, that is z transform, that is x of z equal to minus z into, okay, differential property, minus z into d by dz of x1 of z. Where x1 of z is, what is the x1 of z value is z by z minus 1. So after differentiation with 1 with respect to dz, that is nothing but z minus 1 whole square upon numerator value is u method. So what happened? Z minus 1 into with respect to z now. So it is 1 minus again z minus 1 z is the constant, z into z minus 1 is the for derivative part, that is z. So what is the value of this one? Z minus 1 minus z is coming. So by z minus 1 whole square. So z cancel. Only minus 1 is there. Minus 1 by z minus 1 whole square. So if you multiply this one to inside, what happens? Plus z by z minus 1 whole square is getting. So you have to prove this one now. Okay, you have to prove this one. This is a Z transformation. So differentiation in Z transform. Coming for here, determine the Z transform of x of k equal to 0.5 k minus 0.8 k. First of all, in this function, we are in the two parameters, that is x1 of k and x2 of k. x2 of k. So this is I am taking the x1 of k. It is I am taking the x2 of k. So take this is x1 of k now. So for this one, if you apply, that is 0.5 k. For this one, if you apply z transform, so it is coming to as x1 of z. So what is the value of x1 of z? That is z by z minus 0.5. Z by z minus 0.5. Similarly, for going to second one, x2 of k. So what is the value of this one? That is x2 of k equal to 0.8 k. 0.8 k. If you apply for z transform this one, x2 of z equal to z by z minus 0.8. Z by z minus 0.8. Now coming for the equation, if you see in this one here, we are going to taking the linear property. Linear property, that is already we know x of k equal to x1 minus k, x1 of k minus x2 of k. Similarly, if you apply for this one z transform, x of z is coming to as x1 of z minus x2 of z. That's why it is a linear property. Where coming for the x of s equal to final property, x of s equal to z by z minus 0.8 minus z by z minus 0.8. So okay, if you solving this one, the differential equation, sorry, if you solving this one, taking the LCMs, and after that one we get the value is z square minus 0.8 to z minus z square plus 0.8 to 62 by z minus 0.5 plus z into z minus 0.8. Okay, z into e power minus 8. It is the solution for this one. So this is the transform of the transformer by using linear property. Coming for the another one, differentiation property. Okay, differentiation property. See this one, x of k equal to k into 0.5. For this one, what is the z transform? X of z equal to, in previous formula I have explained now, x of for this one, the z transform will be, that is x1 of z equal to a by z minus 0.1. Z minus 0.1. So what is the function they given? X of k equal to x1 of into x1 of k, k into x1 of k. So x of k equal to minus z into x of k equal to minus z into d by dz of x1 of x. Okay, x1 of z. So this is a differential property. Okay, substitute this one here, minus 2 to d by dz of z minus 0.5. Okay, if you multiply the inside, what happened? 0. It is coming to plus now. So what happened? This is 0 to cancel. Only 0.4 z will be there. 0.4 z will be there. So this is the problem for determining the transfer function of x of k. Okay, determining the transfer function, the transform of x of k. Coming for the third problem. Determine the initial and final values of x of k. Okay, initial and final values of x of k. Already we last class we will see the initial theorem, final value theorem. For that one, we have taken the note today's in class. We have taken the problems. That is, we have the problem is x of z equal to z square plus 3z plus 7. If you take this one, for finding, I am taking the initial value theorem. What is the formula for initial value theorem? X of 0 equal to limit z. Initial value theorem, here x of 0 is there and the limit will be coming to infinity, and the limit is coming to infinity. So taking the limit of infinity and given in transfer function. So what happened? It is coming to as infinity by infinity. Infinity by infinity. So if you are getting the infinity by infinity, we can go into that one. The given function, if I am taking the given function, so that okay, for given function differentiation, what happened? It is coming to as 2z plus 3 by 2z plus minus 4. For this one also I am getting the infinity by infinity. Infinity by infinity. Again we are going to for differentiating. What happened? With respect to z, what happened? This is coming to as 2 by 2. 2z differentiated with respect to z nothing but 2 by 2. Okay, we got that 1. We got that 1. This is the value for the given function initial value theorem. This is the first approach. Now I am going to the second approach. That is x of 0 limit is z tends to infinity. The function is there. So in that one, I am taking the z transform is common. Z square is common I am taking. So what happened? This one coming to as z square is common. 1 plus 3 by z, 3 by z plus 7 by z by 1 minus z. Okay, z square is common here. Same. Z square. Here also z square common. So 1 minus 4 z by z plus 3 by z square. 3 by z square. Yeah, z square. Okay. So if you take that this one, 1 minus, if you substitute the limits here, limit just tend to infinity, no? Here something by infinity nothing but 0. Something by infinity nothing but 0. This one 0, this one 0. Only 2, 1 by 1 is there. So we get the 1 now. Similarly for previous. First approach. Here get the 1, here get the 1. Okay. This is the second approach. Okay. Coming for the next. Coming for the final value theorem. What is the final value theorem? X of infinity equal to limit z tend to 1, z minus 1 into x of z. This is the formula for final value theorem. Substitute the x of z value. That is limit z tends to 1 and z minus 1. That is z square minus plus 3z plus 7 by z square plus minus 4z plus 8. Okay. If you substitute that one is here. So what happened? Limit z tends to 1, z minus 1. So I am taking the in denominator part, that is roots. So what is that one? Z minus 1 minus z minus 3. So what is that one? It is coming to as this one total roots. So after that one, I am taking the limit distance to 1. That is it is and z minus 1 cancel, z minus 1 cancel. Only z minus 3 will be there. So z square plus 2z plus z plus 7 will be there. After that one, limit apply the limit here. So what happened? It is coming to as z tends to 1 now, 1 plus 3, 4, 4 plus 7, 11 by 1 minus 8. That is minus, sorry, 1 minus 3. That is nothing but minus 2. That is we are getting the final value is 5.5. 5.5 minus 5.5. Coming for the next one problem. We will see the linear property problem, and we will see the differentiation problem. And in initial value theorem, we see the differentiation property, and initial value theorem, we will see the differentiation property and linear property, H property rule. So next I am going for the determine the Z transform of this x of z equal to 3z plus s by s square plus 3s plus 2. So we are going for Factor fraction method. Yeah. So what happened? This is the main function. It is a two variable function that is coming to as 3s plus 5. So it is coming to as by x plus 1 into x plus 2. So for taking this for partial fraction, what happened? A by x plus 1. It is x plus 1 denominator. X plus 1 plus b by x plus 2. X plus 2. This is one x plus 2. So if you have find the a value, how can you find the a value? Already we know. This is the shortcut method we know. So total, first of all, for finding the a value, first we take total function. That is 3x plus 5 by, okay, s plus 1 into s plus 2 into what is the multiplication factor? What is the a value, b value? That is s minus 1, no? S minus 1. Make it here. Sorry, s plus 1. Where? What is the value? Make it here. X plus 1 equal to 0, s equal to minus 1. Substitute this s equal to minus 1. So, and here s plus 1 cancel. X equal to minus 1 minus 3 plus 5 by minus 1 plus 2. It is coming as 4 by 1. 4. S equal to minus 1, no? Minus 3 plus 2. It is 2. 2 by 1. We got the 2 value. Next, coming for the b. What is the total function? 3s plus 5 by s plus 1 into s plus 2 into what is the value of b? B equal to nothing but s plus 2. S plus 2. So multiply here s plus 2. What are the limits? Summation limits s equal to minus 2 for this one. S equal to for this one s equal to minus 2. So this one is cancelled. S equal to minus 2 nothing but minus 6 plus 5 by, okay, minus 2 plus 1. That equal to, we are getting as minus 1 here minus 1. So it is getting as 1. We are getting as 1. So these are the factor fraction method by the simple way method. Now, so substitute here x of z equal to okay, a value is 2 no 2 into s nothing but z by z minus e power of minus t, z power of minus e power of minus t. Apply for this one. For this one, substitute the a value and substitute the b value here and apply the z transform. Okay, that is nothing but x of s equal to 2 by s of x equal to 2 by s plus 1 plus 1 by s plus 2. So apply here now z transform. That is nothing but what is the z transform of 1 by s plus a? That is z by z minus e power of minus 80. So similarly, it is coming to us like this. Z2 is there, 2 is there, 2 into z by z minus e power of minus t, e power of minus t. What the value is 1 plus z by okay z by z minus e power of what is the a value is there? A value is minus 2 into t, minus 2 into t. So taking the LCM and solution for the mathematical expression, we got this value. Okay. So this is the determination of Z transform. Here we got the two applications. That is, in this problem, factor fraction method is coming, and then one is by taking the factor fraction method, how can you solve the Z transform equations? Okay. Now I am going to the Z transform of this one by using factor fraction. Again, same. So what happened? We have x of x equal to 2s plus 3 by x square plus 2. For this one, the factor fraction is going to be applicable for this one is a by x square plus b by s plus c by s plus 1. This is the basics already we know. Okay. Now for calculating the a, first of all, a equal to, already I have explained here, but I am writing once again. For the total function, 2s plus 3 by x square into s plus 1 into what the value of the a here inside the equation, in this equation, inside this equation, a value is s square. Sorry, s square. That is nothing but s equal to 0. S equal to 0. So what happened? By into s square and s equal to 0. S square will cancel, s equal to 0, nothing but 0 is there, only 3 is there. Only 3 is there. Okay. Similarly, go for b. So what happened? Here it is derivative of, I am required for b now. So dz of 2z plus 1 into by s plus 1, where s equal to 0. So if you taking this is the derivation of first of all. So we got the expression this one. After that one, if I apply the s of equal to 0, so what happened? 1 by 1 minus square. That is nothing but minus 1 is coming. We are coming for the c value. So that is 2s square, 2s plus 3 by s plus 1 into s plus 1. So s plus 1 will cancel. S plus 1, c equal to c. S plus 1 into, okay, this is for c value now. S plus 1 into, what is c value denominator? 1 plus s plus 1. S plus 1. Where s tends to, what is the denominator value? S tends to minus 1. Up to these values here, so we got the one value. After that one, substitute these values into x of s. We got this value 3 into taking the LCM, we got this value. Okay, t into s, tz by square. Okay, like this. So after this one, if you go for the calculation part, mathematical calculation, we got this one. And after finally the calculation part, we got the Z transform. We got the Z transform like this formation. Okay. Now, coming for the convolution property, one problem. They given as x1 of n equal to 1 by n whole power of n and into U of n and 1 by 5 whole power of n into U of n. First apply for this convolution by first we are going for by convolution property. Apply for this one into Z transform. Okay. Apply for this one is Z transform. That is nothing but for first part Z transform is Z by Z minus 1 by 3. For second part Z transform is Z by Z minus 1 by 5. Okay, 1 by 5. So what is the convolution property here showing? Convolution property is nothing but Z into x of n into x of z equal to Z into x of n1 into x of n equal to, that is nothing but x1 of z into x2 of z. So substitute these values into here. Substitute these values into here. That is what happened. Z inverse of. Okay, Z transform definition. Z inverse of this value into this value. Total two values. After that one, if you take for this one Z transform, so we have to take in the first of all for this one Z transform for this total value, first two equation values. For this one, we got the partial fractions, that is 5 by 2. 5 by 2. So what happened this first second part? For this second part also, the transform is coming to as Laplace transform is coming to as first of all 3 by 2 into given function. Okay. So if you convert this one into Z transform, Z inverse transform, we got it. 5 by 2 is a constant, 1 by 3 whole power of u n into u of 3 by 2 is in carbon, 1 by 5 whole power of n into u of n. Okay, these are the different properties and problems of Z transform. Okay, used to these reference books Ogata, Q and Gopal. Okay, thanking you.
Like, share and subscribe. Hit the bell icon for more updates.